So my name is Chris Rawles, and I'm going to be presenting work that I've been working on with another colleague, Jared Foundry, and both of us are data scientists at Pivotal. And I think everyone here is familiar with what Pivotal does, one of which is we offer a consulting data science practice. And this is essentially sort of an R&D project that's sort of meant to showcase this idea of data science-powered applications for the Internet of Things. And if this seems like a lot of buzzwords, that's okay. I'll go into what the Internet of Things means and what it means in this context. And I also want to start off by saying this relies on a live demo. The Internet's been a little bit dodgy, so we shall see if it'll work. But I'm excited. We'll get through this. Okay, so basically today's talk is going to revolve around basically two parts here. Number one is this real-time data science application. And how it's going to consist is I'm going to go through the app. It's a live demonstration. I'm going to bring up a volunteer and walk through it. And it's going to be a data science problem of basically human movement classification. So it's going to be using smartphone data. And then once we go from there, we're going to dive into the actual guts of it. Like how can a data scientist build an application such as this? And then with this understanding in mind, we can revisit this application and go through it again to have an understanding of what it is. And so this being a demo, it's interesting and fun, but ultimately what we want to figure out is how can we take this framework, how can we take this setup and apply it to like problems that we actually care about on our day-to-day basis. So I'm gonna talk about how we can take this framework and apply it to the Internet of Things, and in this case, more specifically, creating the smart app to prevent oil spill disasters. And the Internet of Things, for those that don't know, is basically using connected devices and sensors to kind of record activities about what's going on in the real world to make observations and predictions. And then finally, I'm going to touch upon another use case related to finance. Great. So yeah, we're going to do a live demonstration. And I have a volunteer. Dormain has graciously volunteered. And again, please everyone cross your fingers that the internet will be behaving.
This is how you cross your fingers.
Double cross. Okay.
Oh, does that cancel out the other cross?
Okay, maybe just do one.
Just one.
Yeah. Okay, so you can just put that in your pocket. You don't have to touch the screen or anything.
Okay. Do I need to close the screen?
No, please don't. Yeah.
Okay.
Just like that. Awesome. Okay, so what we're doing now is I entered a unique key on both this mobile device and the app, and what this is doing is it's streaming accelerometric data at 15 hertz. And basically, like if you move back and forth, you can see it's registering on there, and this is measuring acceleration. So this is kind of fun. This is sort of a dashboard, and we can see live data coming in. Nice. It's a foreboding of what's to come. So now what we're going to do is we're going to actually walk through the process of building a machine learning model. So what we're going to do is we're going to just do a first activity of standing. So it's very boring, but basically what we're doing is we're streaming in live data from the accelerometer at 15 hertz of standing. And we're not doing any modeling or anything right now. We're simply ingesting this data into a data store. And you'll notice it's kind of general, right? Like we could enter any activity we want. We're really only limited by what the mathematics can differentiate. Do you have a second activity?
So this is Atle's Funny Arms.
Funny.
A-T-L-E.
Okay.
It's my Norwegian dance teacher.
A-T-L-E.
College.
Oh, cool.
This is dedicated to him.
Okay, cool. You can go ahead and start doing it.
Okay.
So we're streaming in funny arms, the movement for funny arms, if the internet's working. And again, we're collecting 20 seconds of it because basically we want to be able to learn
You guys can clap
the
if you
activity.
want. There we go.
Awesome.
Double time.
Okay, you
Just
can
kidding.
stop. And then third activity.
Okay, so I'm going to attempt to do the Roger Rabbit.
Okay.
So, you guys remember that? I might hurt myself falling off the stage.
Okay, you good?
Okay, should I go?
Yep. You can go forward with it, yeah. Yeah.
It's better backwards. It's so much better.
If there's enough stage space. Oh, so brought in. Okay, cool. So now we're going to give it up for Domain, everybody. Awesome. So now we're going to build a model. So this is basically hitting an API endpoint to a microservice, which is building our model. And I'll go into all of these details. So with that being said, now we've trained a model, and we should be able to score it in real time. So she could do one of these 3 activities, and it will basically classify what you're doing. So it looks like it might have kind of worked, judging by the internet, but go ahead and try one of the other activities. Well, we can still watch her dance. Okay, well, that's it for the demo. Thanks. The internet's not working, but for me. Thank you very much. But everybody could imagine what would happen. I have a video prepared. So basically, imagine we went through a similar activity with somebody else. I can't quite do full screen. But this is my colleague Scott, a data scientist. His moves aren't quite as good, unfortunately. And so, yeah, we're doing the same process here. And you can see he's basically doing one of these 3 activities. And as he changes it, it will classify it. So, yeah, that's basically the demo. And then let's actually go into the details of this. Like, how can a data scientist build this kind of application? So we all know that the streaming data is coming from the smartphone. It's accelerometric data. We're using WebSockets, and we're streaming it to basically a sensor application. The sensor application has a way to communicate with the training application. And then once we have that, we basically have the scoring application. And the input to the scoring application is 2 things, right? It's the input data from the smartphone, but then it's also a trained model. So when we have these 2 inputs, we can then classify the activity and present this on the dashboard, which is what we're seeing up here. And the way that we've configured it is the training application and the scoring application are both separate microservices. So they're running, let me keep walking through this. So the sensor and dashboard application are Pivotal Cloud Foundry applications running Flask. And then we basically have Redis, which is the data store. So this is the way that we're allowing the sensor and the scoring app to be able to communicate with each other. And then the training application, similarly, is a completely separate application. It's a Flask application, but it's running scikit-learn. And for those of you that don't know, scikit-learn is basically one of the most popular machine learning libraries in Python. It's great. You get every algorithm that you might want. And then we have the scoring application, which again is a completely separate app, and it's running scikit-learn. And the key here is basically in order to access them, everything's decoupled. So if you remember when I hit train an app or build a model, it sent an API request to the training app, and it said, hey, training app, look at the data that we've stored in Redis and build a model, and then save that model and put it back into Redis, persist it into Redis. And again, this is sort of a framework that I chose for an R&D project, and there's many different ways that you could architect this. And so we all know Cloud Foundry. We've actually seen this haiku today. Here's my source code, run it on the cloud for me, I do not care how. And I have to say, like, as a data scientist, this appeals to me, right? Because my day job is not an app developer. My day job is building the best data science, the best machine learning model I can do. And that takes all my time up as it is. So I don't really want to worry as much about sort of a lot of these necessary things that are really important, but like provisioning and binding data services, I want that to be easy. Creating domain routing and load balancing, and continual app checks and restarts. So if I take advantage of Cloud Foundry, I can use CF push and push this this app I've built relatively easily. So jumping into sort of the actual details. So I keep saying this is accelerometric data, 15 hertz. It's an iPhone. We could use any data we want. And one thing I want to note is, of course, the iPhone is just a proxy for, or it's just a type of sensor, but we all know that we could be ingesting sensor data from any single device that we want. But for demonstration purposes, an iPhone or mobile app is obviously nice. And then for the data ingestion, we really need low latency data ingestion. If the demo would have worked exactly as we wanted, we would have real-time response. So as domain changed her movement, we would get a classification in real time. And we're using a WebSocket protocol, socket.io, and then we're ingesting the data into Redis. And Redis was just a choice that we used. It was really easy for me to get spun up. If we wanted to scale this app up to many, many instances and integrate with Cloud Foundry, we have plenty of other options as well. I would actually look at using Gemfire probably instead. And then we're using the store for sort of three key things here, right? You remember when we hit train data, we're collecting this data and storing it. And then once we've actually built a model, we're saving that model as, in this case, a pickle object, but we could choose any format we want. And then we're using micro batch of scoring for the scoring. So as the streaming data is coming in, we can't just stream each data point as it comes in. This is time series data. So we actually use 2-second windows of this raw time series data, and then we're doing transformations on it. And I'll talk a little bit more about that. So in terms of the modeling, there's two crucial things here. There's basically scalable machine learning applications in PCF, consisting of the training app and the scoring app. And with the training app, the goal is obviously building a data-driven model that can differentiate these different activities or motions. And the input here is basically, we have the training data, and then it comes in, and then the inside represents essentially the data science component of, we have this raw sensor data, which basically you can't do anything with that if you're an algorithm. It's just raw data. So that's the feature engineering. And in this case, we did time domain transformations, fast Fourier analysis, and all sorts of, these are relatively common mathematical techniques, but that allows us to basically represent the data in a way that an algorithm can make use of it. And then we used a random forest model, and we saved that final model into our data store. And this, again, is a completely separate, standalone Cloud Foundry application. A little bit into the details of the model building. So we had 20 seconds per training activity. We used a 2-second moving window on the training data. And you can see this is known as a learning curve. So the x-axis is how many seconds of training data, and the y-axis is how good your model is, right? You don't want to have your participants stand up for an hour just to build a model. So 20 seconds, as indicated by the red dot, is sort of the sweet spot between accuracy and practicality. I think it's important to talk about sort of model training approaches here. There's near real-time model training. So anytime you have streaming data coming in, you need to figure out how you're going to build the model. So what we just did was near real-time model training. So we had streaming data come in, we stored it in a micro batch, and then we built a model. So it's almost real-time. You could do real-time model training, which wouldn't be as applicable here, but as every new data point comes in, you update the model with that new data point. And then finally, so again, this is just different strategies for model training if you're going to be building a data science app. And I think the third one is sort of probably one of the most common ones, which is, you use your Hadoop environment or your Spark environment or your Greenplum or Hawk, and you build this really cool model, and then, with a lot of model tuning and calibration, and you spend a couple weeks on it. And then once you've done that, now you can actually score your application. And this is a pretty similar framework to what we saw. You have streaming data coming in. We're doing the feature engineering on that data again. That's giving us a model prediction now. And again, or also the input is that trained model that we built at the top. So we've done that. And then the dashboard's basically hitting this model scoring app and saying, hey, model scoring app, what is the status of this data? What is the of this user? What is the classification? And then it sends back an API response of the model prediction. And so it's kind of important to talk about why do we want to do model scoring as a service? And the big key here is operationalizing our model, and in particularly operationalizing scalable data science applications. So I think a lot of us know that if you use Cloud Foundry, you get a way to scale up your model. You can use auto scaling, which is basically, which could, in this case, could be as the data grows, the model scales. So we could picture, we just use one sensor here, but imagine if we had 100 sensors or 1,000 sensors. We'd want an infrastructure that could handle that. Excuse me. And then application autonomy. So the model application is completely independent of the other applications, which gives you faster development iterations, right? If you just want to make the change to the scoring app, it's just one thing you have to mess with. And of course, if you have faster development iterations, you can get faster feedback loops, which overall just speeds up the entire process. And also multiple applications can access the model scoring app. So again, if you have multiple sensors, you might want to have one sensor app or one scoring app, and they all submit data and they all get responses. Cool, so this is where I was gonna revisit the app. Perhaps I'll show this. We can zoom in a little bit. Cool. Okay, so basically here we're entering the activities. We've hit train model. This is directly taking the data from WebSockets and storing it into our data store. This is for the 3 different activities, and it's basically a key value. And the key is we're telling it what the label is of walking in place, and the value, of course, is the sensor data that's coming in. And we're doing this for the 3 different activities. And then right here, we just clicked build the model. And what this did was it sent an API request, and it said training application, look where we've put the data, build that model, and then store it back into our data store. And then we go to the modeling pipeline, and we're streaming data into our data store, and the scoring application keeps accessing that data and giving us a real-time classification. So I guess why is this important? What is there that's important about this? One of the important things is, as data scientists, we are really, we spend our day job as building these models, our machine learning models, and it's a lot of work. It requires mathematics, and we like playing with data. But in order to actually get it into the real world, that's sort of a whole nother process. It's another step, but it's also very crucial because we want our model to be alive. So this is a framework that can bring our models alive. And in terms of basically taking this framework and using it to solve new data science challenges, I think the Internet of Things is a really compelling one. I think a lot of us know that every industry is generating billions and billions of data points, and all this data is coming in, and we need to be able to make use of it. And one component is building a model and understanding this data, but another component is building an application where human users can interact with the data, get the results in the model, and have input on it. And kind of getting into a specific example, how could we use data to prevent accidents like the Macondo disaster? So for those of you that don't know, the Macondo disaster is the largest oil spill in history, and it was caused by equipment failure. And it turns out that equipment failure it's actually a relatively studied problem, and it's one thing that we can predict using data science. So if you use sensors and you're measuring different details about, let's say, a drill rig and a rotor spinning around, you can measure vibration, and you can measure how fast it's spinning. And you can build a model with a certain type of accuracy telling you the probability of failure. And in the case of something like an oil spill disaster, you might be able to predict ahead of time using sensors and data science, hey, there's something that could be going wrong. And so the way that you do this is by building the smart application. And the reason I say smart application is it's 2 things. We've built our model, and then we put it into the real world where people can interact with it in real time as data is coming in. And so what I'm going to suggest is we can take this framework that I've just talked about and basically generalize it, keep a lot of the things the same, but instead of using sensor data coming from our smartphone, we can use sensor data coming from an oil and gas drill rig. We can use seismic data coming in. We can use drill rig data coming in. We have thousands. I think each drill rig generates, has over 100 different sensors. So there's a lot of data to get here. And then, of course, if we can sense something going wrong, if we have a high probability, hey, of equipment failure, then there's different things we can do if we interface it with an application where we can alert the operator, send a signal to the control system to change operating parameters. There's plenty of things we can do. And one thing I think is interesting as well is sort of the Macondo disaster is like an extreme case, but this could also be useful for just predicting when you want to replace an old part. If you're drilling for oil and gas, it costs them $500,000 in some cases to drill per day. So if you have unplanned downtime, let's say 2 days, that's $1 million. And if you can predict that ahead of time, there's obviously a lot of value in that. And then finally, what I also want to suggest is this doesn't just have to be sensor data coming from a sensor. This framework could be used for basically any data source we want. It could be retail data, credit card information, retail information, and this could be used for, how can retail banks influence cardholders' behavior? And of course, there's all sorts of interesting things you can do with this data, like providing customized services and promotions, next best offer, and there's all sorts of different things that we can do with it. And that's it. That's everything I have. I want to plug a blog that I wrote with Jared that kind of goes into the details of what we talked about. If you're interested, you can just Google scoring as a service Pivotal, and you'll find it. And yeah, that's everything. Yeah, so the training happens before the scoring stage. So the question is, how does the scoring fit into the training stage? So the training is where the first part where you're learning sort of the general, the differentiating factors between the two movements. And then once you've done the mathematics and you've learned those characteristics, the scoring is we've taken those learned patterns and applying them to new unseen data.
So that can happen behind the scenes in your lab. You didn't like compare it and say that, hey, how well are you? So when you kind of predict the movement that's happening after scoring is already done, it's not like you're saying, oh yeah, you did a great job predicting this.
So the time where you would see you did a great job is where you do the activity and it's flashing across the screen and telling you. So as you're doing the dance, it'll tell you what you're doing, and the way that you would quantify it is basically how well it's quantifying it per second.
This almost makes sense. I think it almost sounds like what you're suggesting is yet another service you might do, which is the post-evaluation of the model's accuracy.
Yeah, I mean, I think that's definitely possible. Yeah, definitely.
So how many instances of training app you have like in this demo app? Just one instance or multiple?
Yeah, and the question is how many instances of the training app in this demo, and there's one instance in this case.
Okay, so if like there are millions of data points, you will still have like one instance, or you can have multiple instances of training app, because the reason why I'm asking is like there could be, we are building a model and probably if we split the traffic across multiple instances, would our model be still accurate? Or we still want to have like one app?
Yeah, I mean, definitely the idea with this is you can scale it up. And so that training cell, we can make more copies of them. And as data comes in, each cell is identical. So data comes in, model comes out. So we would definitely want to scale it up as more data comes in and the load becomes too much.
So for instance, like we are capturing the data every 2 seconds and we are feeding that to a single instance of the app. So app is kind of like learning from that
Yeah.
training for 20 seconds.
Yeah.
But in case if there are like multiple instances, would we still capture the data for 20 seconds or probably we have to increase that?
Yeah, I mean, I think it definitely depends on the problem. Like for this problem, you can get away with 20 seconds per activity, but if we go to that more specific case of the oil and gas well and we want to try to predict equipment failure, that's obviously a much harder problem. And you would want days to weeks to even years of training data.
The graph that we had with the time, 20 seconds and percentage of learning curve
Yeah,
graph, is that percentage the accuracy prediction percentage?
yeah. I think I saw a question over here.
So I'm interested in the banking example that you gave.
Yeah, for sure.
Can you expand on that a little bit? I mean, this was talking about sensors. Are you thinking of different types of sensors that you can deploy? What types of sensors?
Yeah, so the point I was making with the banking app is it doesn't necessarily have to be sensor data. So it could be, if let's say you have your large bank and you have every one of your customers has your mobile app. You can find out, I guess you are getting sensor data about longitude, latitude, where they're checking in, recent purchases. So that might not be coming from a sensor, but it's coming from your database. And that's going into the model. And you might want a real-time decision where if somebody walks into a store and maybe they have a history at shopping at XYZ, they've made these purchases, you need to provide that decision. You only have a certain amount of window where you can give them. And so we don't need to use sensor data necessarily. Absolutely. I'm saying, but we could incorporate non-sensor data as well.
That's being done today. So what's different about this versus what's being done today? And there are companies that use geolocation to do offers. Right?
Yeah, absolutely. I think one of the things is sort of the ease of implementation in terms of spinning this up and building out a scalable application. I think part of it is just this makes it very easy for the data scientist and the developer to build this application and iterate rapidly and get feedback really quickly and make changes to it. You don't need to. We heard somebody talking about development or release cycles once every 2.5 months.
Right.
In this kind of architecture, you're not going to need that.
So it's iteration.
Yeah.
I guess that your last point is sort of my question. How do you engage your data scientists? I guess you sort of said one way is treat these as services, do the model training first, iterate through that, iterate through the scoring. So our data scientists, they're working on SaaS, they're doing gather all world, it's very difficult to get their tools into this mental model thing. What's the best approach? Maybe this is one way, one suggestion.
Yeah. Oh, so I'm at 1 minute. I mean, I guess one thing that we talked about here is they can build their model in whatever environment they want, but or most environments, and then you can still operationalize it using this framework. So they can, build it themselves. I guess last question. If there's just a few samples, how can you deal with overfitting? Yeah, that's definitely a problem in data science. You can never have enough data. In this case, I tested it using different motions, and there wasn't overfitting, but it's always something that you have to worry about. Are you learning the actual underlying pattern, or are you just learning specific data points corresponding to movements? And so different ways that you would do that is doing cross-validation on your model ahead of time and making sure on subsets of the data you're still getting good results. Great. Thank you, everybody.